for the use in our appropriate circuit, we need to know this grouping of capacitors. When they are used, or not necessarily all the time the desired value we are going to get. So that's why we have to design from the given value of the capacitance, we can get the desired value of the capacitance. So to that thing, we need to know the concept of your series and parallel grouping. So see, I took three different capacitors. C1, C2, C3 are their capacitances. So this type of connection is called your series connection. Let me explain you why it is called series connection and why this kind of connection is called parallel connection. Actually, your series connection is what? It's a back-to-back or cascaded style connection. Clear? So I took three capacitors and one battery is connected across these capacitors. C1, C2, C3, and all of you just see here. Here I took C1 and it's the first plate of C1, this is the second plate. Similarly, C2, it is the first plate of your C2, the second plate. Similarly, it is first plate and it is second plate. Why that is so called? Let me tell you, explain. You know the charging process. Already I have told you how the capacitor gets charged. Again, let me tell you, when this is connected to through this battery, the electrons will flow to this terminal. And it will means electron means, let's say it is charging this plate by an amount of minus Q. Earlier it was neutral, all the capacitors were neutral. When the battery gets connected, charges starts flowing to this plate, and this plate, let's say it is charged by a minus Q amount. Since this plate is connected directly to the negative terminal, this plate gets charged, and there is a gap between these two plates of the third capacitor. Means there is no flow of charge, because this plate produces a field which induces a charge here, and equal amount of induction takes place. So here, but opposite, if here it is minus Q charge, you are going to get a plus Q amount of charge in this at the near end. And try to understand this plate, earlier it was electrically neutral, so equal amount of negative charge also developed, but it will try to remain as far as possible from this plate. Clear? That's why there is a interconnection between these two plates, and this negative charge of the third capacitor, it will flow to this plate of the capacitor. Clear? Similar thing occur here, and this negative charge flows here, and since again the similar thing will occur here. So the negative charge, as the positive terminal is connected to this plate, so all the negative charges flow here, and means whatever charge comes to the circuit, the same charge again return to the positive terminal of the battery. So in this process, actually this battery is sending Q amount of charge to this plate, and but for all of you just see, the third capacitors, only one plate is connected to the battery, and this plate is not connected to the battery. But how it is charged then? The charging of this plate is because of your induction. Clear? And this plate is charged because some negative charge, it flows from this plate to this plate, an equal amount of charge will come here. Mean that's because of that reason all the capacitors, they have equal charge in a series connection. And one more thing we can say, if you consider this plate to be 1, means C1's first plate, second plate, C2's first plate, second plate. Why? Because first plate we took all the positive charged plates, and second plates all are negatively charged plates, and they are interconnected. All of you just see, the second plate of the first capacitor is connected to the first plate of the second capacitor. Similarly, the second plate of the second capacitor is connected to the first plate of the third capacitor. It's a cascaded style, means back-to-back connection. That's why it is called your series connection. But the most important part is here, because all are in series, their charges remain the same. That's why they are called series grouped capacitor. Now, this is a reduced circuit of that. In that case, what I have done, I replace all the three capacitors with a single capacitor. The single capacitor will solve the purpose of all the three capacitors. If it solves, then the capacity of this capacitor is called your effective capacitance. I mark that effective capacitance to be your Cs. Why? Because they are series connection. And why? See, whatever all the three capacitors are doing, the single capacitor is doing the same thing. How? Let us see. This battery is sending Q amount of charge to the whole circuit, maintaining a potential difference across this entire circuit to be your V. Now the same capacitor I took, another capacitor Cs, whose capacity is Cs, that is also holding the same amount of charge, and the potential difference between A and B is also V. Means our purpose is solved. That's why the Cs is called your effective capacitance. Now our aim is to calculate if this 3 is to be replaced by a single capacitor, what is its effective capacitance. Now since we got the idea here, the charge remains the same. Now what I have done, I took the potential difference across VAB to be V. Now we can say this VAB is the sum of the potential difference across AC, CD plus DB according to our general formula. That's what I have written here. AC is the potential difference across your first capacitor, that I took V1. Similarly for this I took V2. For this I took V3. Means net V is equal to V1 plus V2 plus V3. Now we know the formula for C is equal to Q by V. So V is equal to Q by C. Now comes here, as all the charges are equal, means all the capacitor's charges are same. So we can replace by that formula. Instead of V here, we can write the charge is Q and the capacity is C. So V is equal to Q by Cs, we can write. So instead of V, I substitute Q by Cs. Similarly for V1, I can write Q by C1 plus for V2 that is Q by C2 and plus for V3 that is Q by C3. Now you take Q common and cancel, and I am going to get 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Now for n number of capacitors, that you can write the same formula here. So remember here one formula, if all the capacitors are identical, C1, C2 up to Cn, then you can get n number of this. So your formula would become 1 by Cs would be n by C, and your Cs is equal to C by n. That you remember. If n number of identical capacitors are connected in series, then the effective capacitance would be 1 by n times of a particular capacitance. Got? And you remember the formula for two capacitors connected in series having capacity C1 and C2. Their effective capacitance would be C1 C2 by C1 plus C2. That's a quick formula to remember. Now let us come to your parallel grouping. The difference between that two is, see, here I took two different capacitors during C2. They are connected to a battery V whose potential difference is V. Means this point is connected here and this point is connected here. So no need to discuss the charging process again. The same thing here. As the battery, let's say the battery is sending some amount of charge here. The negative terminal is sending some amount of charge to this point. As there is a bifurcation, so some amount of charge reaches the plate of the first capacitor, that is Q1, and here it is reaching some charge, that is Q2. So the total charge sent by this battery is the sum of Q1 plus Q2, as it is sending minus, so the charge will be, total charge will be minus Q1 plus Q2. By the induction method, this process, this plate gets charged by an amount, equal amount of positive charge, and the negative charge from both the plates of both the capacitor, they come to here and they reaches to the positive terminal of the battery. Means the battery sends Q1 plus Q2 amount of charge and it receives. So the charge, the total amount of charge at this point is splitted. Got? And these two capacitors, they are connected. They are connected across two common points. One point is A, another point is B. Why they are parallel? All of you just see the the first plate of both the capacitors, they are tapped to a particular point, means they are connected to a particular terminal A, and the other plate they are connected to the another point. That's why these two, they are connected, they are said to be connected in a parallel grouping. Now we can replace this diagram by effective diagram. You can say the reduced diagram here. I replace this both the capacitors by a single capacitor whose capacity is Cs, there will be, you can take it to be a Cp as parallel. and whose purpose is to replace that and do the same job as both the capacitors were doing. Now both the capacitors, they are receiving Q1 plus Q2 amount of charge. Here this capacitance also doing the same amount of charge, keeping the potential difference across it to be your V. Now we can find, and the idea here, if capacitors they are connected in parallel grouping, they have the potential difference same. Now the total amount of charge here, including both the capacitors, we can say this Q1 plus Q2, which is Q I took here. In this case, Q1 plus Q2, the total charge is Q. If it will be Q, and in this formula we can use Q is equal to CV. So your effective capacitance is Cp. So Q is equal to C into V. Instead of C, I have just written Cp into V. For Q1, this one, that is C1 into V, and for Q2, that is C2 into V. Why V? Because potential difference across all the capacitors will remain same. Now V is common, you can cancel out, so you can get the answer Cp is equal to C1 plus C2. And if n number of capacitors are connected, this term would have been extended up to Cn, means C1, Cp is equal to C1 plus C2 plus C3 up to Cn. If n identical capacitors are connected in series, then you would have get the formula Cp is equal to, means C plus C plus C up to nth term, and your answer would be Nc. Means overall you see here in series grouping the effective capacity decreases, and in a parallel grouping the effective capacitance increases. So this is the overall grouping of capacitors. Thank you.